Welcome, Mechanics of Materials students. This is the second of two lectures on state of stress for axial loading. And in our first lecture, we defined stress in its most simplistic definition as the force per unit cross-sectional area, where that cross-sectional area is has a surface normal that's parallel to the direction of application of stress and is defined as axial stress. And then strain being defined as the change in length in the direction of stress application divided by the original length. We went from there to describe how a load elongation relationship included material properties and the geometry of the body, especially its original length and cross-sectional area, versus a stress versus strain relationship, which basically canceled out the geometric factors, leaving only the material properties, which could be summarized by inelastic modulus. For small strains, small applied stresses, that modulus is a constant, so we have a linear relationship. We rearranged those terms to give ourselves an effective spring constant, so we could directly relate the force to the elongation via terms that were either defined by the geometry of the body or were something we could look up. The elastic modulus, Young's modulus is another name for it, in a table of material constants, and how we could use that relationship and some way of measuring or relating strains and elongations, something we could measure or relate, to create another equation of equilibrium and apply that to statically indeterminate systems that we couldn't solve with just statics. So we've barely scratched the surface of stress-strain relationships, and we're already applying it to solve more problems that we couldn't solve before in statics. So we're going to continue that same concept with two more example problems. And then for future lectures, we're going to dig deeper into definitions of stress. We're going to include shear, and we're going to look at stress at a single point, which is the real concept that we'll leverage going forward to apply in more general scenarios. Okay. In the meantime, we have a little table. This is a granite slab being supported on some wood legs. This is supposedly going to be used for to put a microscope or some kind of vibration-sensitive measurement instrument on. This is kind of common, the granite slab tables. And we're told that the granite slab is it ends up weighing 5.4 kilonewtons. It's 1/10 of a meter thick and 1 meter by 2 meters. The initial length of all of the table legs is 1 meter, and we don't know the cross-sectional area of each leg. We're going to end up solving for that. We are told that the legs are Douglas fir, typical furniture material. Today that's a little bit old-fashioned. Today it would probably be some kind of polymer, or more likely metal. We do know that some types of wood are a little bit more vibration dampening. Maybe that's why it was picked, but that's what we got. Someone's asking us for a cross-sectional area. We got to make sure that we can support the slab weight, and we need to make sure that we meet the natural bench frequency requirements. Remember, this is a vibration table. So we're told, for a table like this, the frequency of vibration is going to be 1/2 pi times the square root of this spring constant divided by the mass of the table. And given how much heavier the granite is than the legs, we're going to assume that that mass is equal to the mass of the granite. And we're told whatever this ends up being, it better be more than 100 hertz. Okay. And in this case, the K is the spring constant of the sum of all 4 table legs working together. So there's kind of like 4 parallel springs attached to this weight. And so it'll have a natural vibrational frequency defined this way, and we're given a kind of a lower limit. It has to be at least that much. And we've got to exceed the compressional, the area has to be such that we're not applying more compressional stress than the wood can withstand failing compression. Okay, so we got 2 design criteria we got to meet. So we can start with a statics problem. Let's take the granite slab and put it in static equilibrium. So its weight downward is going to be opposed by 4 equally spaced, give or take, forces coming from the table legs. Not quite equally spaced because it's 2 meters on one side. But they're all going to end up having the same reaction force. We're told that they're all the same cross-sectional area and same length, same material. So we're going to have a uniform situation here. So it's not like the previous problem where we had to assume that each of those forces could be different or some could be different, and we were solving for the relationship. This time we know they're all the same. So we have 5.4 kilonewtons of mass of the granite being held up by 4 times the force of the table leg. So each table leg has to be exerting 1.35 kilonewtons. So we don't want them to fail. So we go, well, what is the maximum compressive stress of this Douglas fir? Well, we look it up in a handbook and we find it's 8.3 megapascals. So that's 8.3 times 10 to the 6 newtons per square meter. So we know that that's equals the force divided by the cross-sectional area. So the cross-sectional area is going to be the force divided by the maximum compression stress. So that means our area, our cross-sectional area, is something about 1.6 times 10 to the minus 4 square meters. Generally speaking, we would use the area of a circle and calculate a minimum diameter from that. But we know we can do that, so we're just going to work with areas. So now we know that's a minimum. We got to make sure that the frequency requirement doesn't impose a bigger one. This is the minimum area the leg can be. It can be bigger, no problem. That'll just give us a safety factor against failure. So we got to make sure that this spring constant effect doesn't drive us to an even bigger table leg. Okay, so let's look at how this effective spring constant adds up, because we're going to plug into this natural frequency formula for K leg. Let's go back to where it was originally given. We were given 1 over 2 pi K over M, where M is the mass. We can assume M is the mass of the granite table, and K is the spring constant of the legs acting in concert. Okay. So let's look at how the springs act together. They're acting in parallel. You got one attached to each corner of the table. So to lift the table up or push it down, which is what would happen during vibration, we're stretching all 4 springs simultaneously. So their effective constants are additive in this case. So K, the spring constant for the whole table, is going to equal K times the effective spring constant of any one leg. So we can zip 4 times K leg into our natural frequency formula that we were given. So we can say that 1 over 2 pi times 4 times the spring constant per individual leg divided by the mass of the granite, square root, has to be no less than 100 hertz. We can get the mass of the granite by just taking its weight, dividing out gravity. It turns out to be 550 kilos, which is pretty simple. So we can back out an expression using the 100 hertz for K leg. Now we have to relate that to something having to do with areas, moduli, and other things that we can use to design the leg. Now we can drop back here to our base expression for the effective spring constant of this leg. in terms of force, modulus, cross-sectional area, which we derived in the previous lecture. So we know that the spring constant, quote unquote, of any body is the material elastic modulus, which is going to be the modulus of Douglas fir in this case, times the cross-sectional area, which we know has to be at least 1.6 times 10 to the minus 4 square meters, divided by the original length. This time we're not necessarily solving for an elongation, a compression this time. We just need the whole spring constant. So we know that K leg is going to be set by the solution to this equation. So we can just basically drop K leg in here, do some algebra. So 100 hertz is 1 over 2 pi times modulus of Douglas fir, which we've looked up, and is 12 times 10 to the 9th pascals. That's 10 to the 9th newtons per square meter. Moduli are big when they're expressed in SI units, which is pascals or newtons per square meter. So expect to see elastic moduli in the gigapascals range. We have our area of the leg, which we're solving for again to see if it's bigger than what we needed just to prevent compressive failure, and our original length, and then that'll be times the mass of the granite down here. So we're just plugging and chugging into our given natural frequency formula, which someone gave us. Okay, so we solve for a leg, and we get 4.5 times 10 to the minus 3 square meters. Whoa, like that's more than an order of magnitude greater. So it turns out we need a much bigger area, cross-sectional area of table leg to ensure that that natural frequency is above this 100 hertz minimum. So it turns out to be the frequency requirement that determines our minimum leg diameter. So we need a much bigger fir cylinder to make the table leg. So in that case, we leverage the definition of stiffness in terms of modulus and our geometric factors directly, because we needed what's effectively a spring constant to relate to some vibrational characteristic. So for our last example, we're going to go back and look at something closer to our first one, where we're using the idea of stress and strain, load versus elongation, to figure out what resultant forces we needed. So in this case, we have a boom winch, a boom crane and a winch. So we have a hinge at C attached to some immovable surface, and a boom. So this boom can rotate about point C. We have a cable that's attached to point B to a winch at point A, so it can be applied to rotate this boom around C. And then we have a cable from point B to D holding a weight. And so in this scenario, the weight's sitting on the ground initially, and someone turns the winch and the boom rotates up such that there's no slack in cable AB or in the cable connecting B to the weighted D, and it's just barely off the ground. It hasn't been lifted up much, but we're not getting any support from the ground for the weight. So the weight is the big square weight is being carried entirely by that cable. So if we did an FBD of the weight, the tension in cable going up at point D is going to be equal to W. So we're told that the cable is some kind of steel, and that it has a cross-sectional area of 20 square millimeters, and we want to know how much the boom's going to rotate. And for this, an important point that needs to be clarified, and that if you were doing this in the field, you'd want to go out with an observation. This is not necessarily a continuous cable going from D to B and to A. If it is, we can assume that it can support some frictional losses. So we have a force W going downwards on the end of the boom and cable tension B to A in the direction of the cable, which will depend on how much the boom rotated. If it were a continuous cable going over some kind of frictionless support, those would of course be the same value. Okay, so we're going to start with statics. We're going to FBD the boom. And we're going to include its rotation angle versus what it started with, which we would determine with these three feet measurements. 3 by 6 determine this original angle theta. So we're going to go ahead and which was originally 45, and we're going to write an expression for a change in alpha as a result. So we start by assuming the crane's already rotated a little bit, so we don't know quite what alpha is going to end up being, but we can write an expression for the sum of the forces in terms of alpha. We're going to assume that we stay at 45 degrees with our angle theta. So FBDing this, we know we're going to have we have a hinge at C, so it can't provide any rotation. It can't provide a moment in this case, and we know that the boom is going to act like a two-force member in this case. So the sum of the resolved forces of T and W are going to have to be in line with C. So we know that the force coming from that hinge is going to have to act in a direction parallel to the boom in this case. So this is all just using our concepts of statics to solve for this. So we have F sub C acting up with our original angle theta, and then we have T acting at an angle alpha to the horizontal, and then W acting always vertically downward because the weight's hanging straight down from it. So we're going to do a sum of the forces in the X and the Y. So we can say that our T cosine alpha is in the positive X direction, and then we have the cosine of 45 for our resolved net hinge force acting at C going in the opposite direction. Looking at the Y component, of course we have the weight hanging straight down. Negative, we have negative T sine theta, or excuse me, sine alpha coming from the cable, and then that's being opposed by the upward cosine 45, same as sine 45, coming from the hinge. So the hinge is kind of opposing both. So that's kind of our initial state. Take a quick pause. Okay, so in terms of what we do and don't know from these two equations, we can use the fact that we have a two-force member. We can solve in terms of W, eliminating F sub C, and we can get a value for T with and alpha together, with alpha being 26.6 degrees and T at 22.4 kilonewtons. I'm going to add another detail that I missed when I started into my boom FBD, and that changes the picture of what I've said to date, and apologies for the lack of clarity there. The alpha initial is 26.6 degrees. The FBD of the boom occurred prior to the stretch of the cable. So we're looking at what the boom configuration would look like after the weight is applied but before the cable stretches. We're going to assume a very small stretch. Probably wondering how I managed to solve for this many equations and unknowns. We knew alpha from the original geometry, and that allowed us to get T of 22.4 kilonewtons. So we crank the winch around, we look at the instant in time, which is really not applicable because elastic deformation tends to be, it's instantaneous pretty much, but we're kind of doing a thought experiment where we look at the initial geometry and then we let everything stretch a little bit and then calculate the resultant strains, look at the elastic relationship, force, elongation that would be necessary to get that. So we're doing kind of a two-step that would be all in one in what actually happens, given that there is no lag time of load versus elongation with elastic deformation. So our 22.6 did not come from the cable stretching, it came from before the cable stretched. So it was a simple FBD with alpha as known and F sub C and T as the two unknowns. And so we had two equations and two unknowns. So alpha was the original angle that the tension cable made. So now we can take that 22.4 kilonewtons and we can say, okay, I know the material, I know the original length of the cable, I know its cross-sectional area, what's its stress, what's its strain, how much is it going to stretch. So easy, I've got an area, I've got a force, so I can calculate stress. So I put my 22.4 kilonewtons up here. I take 22 square millimeters. This is equal to 20 effectively times 10 to the minus 6 meters. That's my cross-sectional area. I divide the force by the cross-sectional area. I get a stress. I can look up the modulus of steel in SI units. It's 200 gigapascals. And I know that the strain in the cable, the stretch divided by the original length, is going to be equal to the stress, force per unit area, divided by the modulus, and then flipped. So strain times modulus equals stress. So my strain in the cable is the stress that I just calculated, divided by the modulus that I looked up, and we can see that the units cancel out. I get dimensionless units, known units for strain, and it should be something fairly small. If you end up getting something more than one for strain, that means that you applied a tensile stress and the thing got bigger, which only happens very rarely. Definitely not in this case. So the fact that we got something that is in a 10 to the minus 3 range is reasonable. So now we say, well, I know strain. If I want the change in length, which will give me the change in the angle of the boom, I need to know what the initial length of the cable was. So I come back up and I use the length of the boom, which is square root of 18, 3 squared plus 3 squared, square root Pythagorean, and then I can calculate that by properties basically of triangles of geometry. Well, assuming the winch is very short, so we basically have a big triangle here with our BC to winch angle much greater than 90 degrees. But we can use that to calculate the original length and then use the change in that B to A length. Let me drop the view so we can scroll down a little bit more. So I use that change from my original length of 6.708 meters in winch to point B to 6.708 meters plus the delta L. So this is the strain times L0 So this whole term is delta L. So basically I defined the angle, I let the cable stretch, and now the boom is sitting at a different angle. So I can use some geometry to basically solve for the new angle BCA and find that it's 135 degrees originally versus 136.6, so the rotation was 1.6 degrees. So a little bit of triangle geometry might need to be looked up, but that's very basic. So key points, what did we use? We started with looking at the geometry of the problem. We did an FBD of the original state. We didn't let anything change length. So we solved for forces without allowing any elongation. Then we allowed some elongation and we calculated the resultant change in geometry. Now, something you'll notice, if we use the new geometry, that original FBD would no longer be valid because alpha would have changed, and we used alpha to get T, which we used to get a new alpha iteratively. So if we wanted to be very, very accurate, we would have gone back and recalculated a new T based on the new alpha and then gone back and forth until there was almost no change between. As it stands, 1.6 degrees, if we went back and when we calculated an alpha of, calculated T with an alpha of 25 degrees instead of 26.6, there would be almost no change. So the fact that we didn't go back and revise our answer for the changed geometry is one of those small strain approximations. For something that's bigger, we might need to do that and then keep going until the difference in our answer is less than some tolerable error. But that's why we were able to use the unstrained geometry to calculate the force that we used to get the strain, which changed the original geometry. That is a little bit erroneous, but the key takeaway is a little bit. So the error induced by that approximation is small, and if we wanted to reduce it, all we would have to do is go back and recalculate a new T with the new alpha, and then dump that in and get the new change in angle. But generally speaking, for something small, which is what we'll typically have in that elastic range, and that's one of the things that we'll count on as we go forward with elastic deformations. They're small strains. So that means small geometrical changes, which means these types of approximations that don't require us to go back and iteratively refine our answers are usually valid on the first pass through. So that is it for axial stress strain. Introduction to definition of stress and definition of strain, definition of modulus for axial loading and deformation, and a very handy-dandy application of those very simple definitions to solve statically indeterminate problems with certain configurations. For our next lecture on stress, we're going to dive into stress in terms of material properties. We're going to look at stress state of a small volume element and look at both axial and shear stresses and how they relate to that volume element being in equilibrium, which is a concept we can move forward and relate to just about everything for the rest of the course. So stay tuned.